5 minutes spent reading about this particular story genuinely isn't enough time to fully grasp it, because what James Webb actually picked up from beyond our solar system isn't a radio signal, isn't a beam, isn't anything artificial at all. It's something far stranger, a subtle chemical fingerprint tucked inside starlight that, here on Earth, is only ever reliably produced by living things. Quick thing before we go any further, subscribe now, because the real story here has more genuine twists and turns than the headlines ever let on. Before we dig into what was actually found, it helps to understand the instrument that made this whole debate possible in the first place. The James Webb Space Telescope launched in December 2021 and now orbits roughly 1.5 million kilometers from Earth, parked at a stable spot in space called the second Lagrange point. Webb is an infrared telescope, built specifically to pick up faint heat signatures and stretched out light from extremely distant, extremely faint objects, which also happens to make it exceptionally good at a completely different job, studying the atmospheres of planets orbiting other stars. When a planet passes directly in front of its host star from our vantage point, a moment astronomers call a transit, a small fraction of the starlight passes straight through the planet's atmosphere on its way to Earth. As that light travels through, different gases in the atmosphere absorb very specific, precise wavelengths, carving tiny dips into the overall spectrum of light Webb eventually picks up. By carefully measuring exactly where those dips show up and how deep they run, scientists can work out which molecules are present in a distant planet's atmosphere, and roughly in what quantities, without ever needing to send a spacecraft anywhere near the planet itself. This technique, called transmission spectroscopy, is exactly how every single result we're about to walk through was actually obtained. Let's start with where this signal is actually coming from. The planet at the center of this story is called K2-18b, and it sits roughly 124 light-years from Earth, inside the constellation Leo. It orbits a small, cool, quiet red dwarf star, completing one full trip around that star in just about 33 days. Despite that very short orbit, K2-18b actually sits quite comfortably inside its star's habitable zone, the region around a star where temperatures could allow liquid water to exist, because red dwarf stars are so much cooler and dimmer than our own sun. In terms of size, K2-18b is considerably bigger than Earth, roughly 2.6 times Earth's radius and about 8.6 times Earth's mass, which places it in a category of planet we don't actually have any direct examples of anywhere in our own solar system. Scientists broadly call it a sub-Neptune, meaning it falls somewhere between the size of rocky Earth and the much larger ice giant Neptune. Back in 2019, early observations of K2-18b, using a combination of the Hubble Space Telescope and other instruments, suggested it might have water vapor in its atmosphere, sparking early excitement about its potential habitability. Later, more careful analysis called that original water vapor detection into question, showing it may actually have been methane instead. An early reminder that this particular planet has a long history of exciting announcements, followed by more careful, more cautious scientific double-checking. Then, in 2023, the James Webb Space Telescope turned its instruments toward K2-18b and delivered a much clearer picture. Webb confirmed the presence of methane and carbon dioxide in the planet's atmosphere, while also finding a surprising lack of ammonia. This particular combination matters because it lines up with a theoretical model proposed by astrophysicist Niku Madhusudan at the University of Cambridge, describing a type of planet he named a Hycean World, short for hydrogen and ocean. A Hycean world, in this model, would have a thick, hydrogen-rich atmosphere sitting above a deep, planet-wide ocean of liquid water. The low ammonia levels matter specifically because ammonia dissolves easily into water, so finding very little of it in the atmosphere fits with the idea that a large ocean underneath could be quietly absorbing it. This 2023 result alone was already a major deal in exoplanet science, marking the first confident detection of carbon-based molecules in the atmosphere of a habitable zone exoplanet. But the moment that truly launched K2-18b into worldwide headlines came in April 2025. Using Webb's mid-infrared instrument called MIRI, Madhusudan's team announced they detected chemical fingerprints matching either dimethyl sulfide, known as DMS, or a closely related molecule called dimethyl disulfide, known as DMDS, inside K2-18b's atmosphere. Why the stir? Because on Earth, DMS and DMDS are produced almost exclusively by living organisms, mainly marine phytoplankton and certain types of marine algae. There are very few known ways to naturally produce these particular molecules without biology being involved somewhere along the way. The University of Cambridge's press release called this the strongest evidence yet that life might exist on a planet outside our solar system. Headlines around the world ran with it almost instantly, and it's easy to see why. This was, and still is, one of the most tantalizing results in the entire history of the search for life beyond Earth. However, and this is the part most headline-driven coverage conveniently skips, the scientific community's response was immediate, cautious, and in many cases, openly skeptical. Just days after the announcement, Jake Taylor, an astrophysicist at the University of Oxford who studies exoplanet atmospheres using Webb, ran his own independent reanalysis of the exact same raw data. His conclusion was blunt. He found no statistically significant evidence supporting the DMS or DMDS detection at all. This wasn't a lone dissenting voice either. Over the following months, multiple independent research teams, including researchers named Luque, Wellbanks, Schmidt, and Stevenson, among others, each ran their own separate analyses of the same MIRI data, using different modeling approaches and different assumptions. Several of these independent studies reached the same conclusion as Taylor, that the supposed DMS or DMDS signal sat right at the edge of the instrument's noise floor, meaning it was statistically indistinguishable from random measurement noise, rather than a confident detection of any specific molecule. One especially thorough follow-up effort, described in a study covering the near-infrared and mid-infrared data together, expanded the search dramatically, testing the observed spectrum against a library of 661 different candidate molecules individually. This was an attempt to systematically identify every plausible chemical explanation for the observed pattern rather than focusing narrowly on DMS and DMDS alone, and to check the robustness of the original claim using 3 separate, independently built analysis codes running on the same underlying dataset. One particularly detailed study, published later in 2025, dug even deeper into why different research groups kept arriving at noticeably different answers from analyzing the same underlying dataset. This was an important question in its own right, since it goes directly to how reliable and repeatable the original claimed result actually was. That study found that the apparent DMS or DMDS signal appeared to be an artifact created by a specific technical choice in how the raw data was grouped for analysis, a process called binning. Researchers tested many different reasonable binning configurations and found that only a small fraction of those configurations, roughly 1 in 8, actually produced results supporting a DMS or DMDS detection at all. In other words, depending on exactly how you sliced up the same raw numbers, you could either find weak hints of these molecules or find nothing at all, which is a serious red flag in careful scientific analysis. That same study also found that other completely different molecules, including one called ethylene and another called chloroethane, fit the observed data at least as well as DMS or DMDS did, sometimes even better. This means the original signal, even if it is real and not just noise, can't currently be confidently attributed to any one specific molecule. In July 2025, a separate NASA-led study added yet another layer to this ongoing scientific back and forth. This team specifically set out to compare results across multiple research groups using multiple modeling approaches, aiming to figure out which conclusions about K2-18b's atmosphere held steady no matter which method was used, and which ones shifted depending on the specific assumptions each team made. Their findings painted what researchers described as a nuanced picture. They confirmed, with reasonably strong confidence across nearly every method tested, that K2-18b really does have a water-rich atmosphere, with water potentially making up as much as half of the atmosphere's total mass, along with confirmed methane and carbon dioxide. However, this same NASA-led study found no conclusive evidence supporting the presence of DMS specifically, essentially tempering, without fully ruling out, the excitement generated by the original April 2025 announcement. So where does all this leave us? As of the most recent, most careful, most independently checked analysis available, the honest answer is that K2-18b almost certainly does have a genuinely interesting water-rich atmosphere containing methane and carbon dioxide, a chemical combination that remains scientifically consistent with the Hycean World hypothesis first proposed by Madhusudan. But the specific headline-grabbing detection of DMS or DMDS, the part of the story most closely tied to the phrase possible sign of alien life, currently doesn't meet the rigorous statistical bar the scientific community requires before confidently announcing a biosignature detection. Multiple careful, independent reanalyses of the exact same raw Webb data have consistently found that the supposed signal is either statistically insignificant, likely explainable by other non-biological molecules, or dependent on specific, somewhat arbitrary technical choices made during the analysis process. This entire episode is actually a genuinely valuable case study in exactly how careful, rigorous science is supposed to work, even when the initial headlines outrun the underlying evidence. A team makes a bold, exciting claim based on genuinely real data. Independent researchers immediately reanalyze that same data using different methods to check whether the result holds up. Some groups agree, some disagree, and everyone publishes their reasoning openly. So other scientists, and eventually the public, can follow exactly how the conclusion was reached. Astrobiology, the field dedicated to studying the possibility of life beyond Earth, has been through cycles like this before, and each time, the process of open scientific debate and independent verification has proven essential for separating a genuinely important discovery from a statistical false alarm. Researchers involved in the K2-18b debate have pointed out that this situation closely echoes two earlier cases in the history of astrobiology. In 2020, a research team announced a potential detection of phosphine gas in the thick clouds of Venus, initially framed as a possible sign of microbial life floating in that planet's atmosphere, only for follow-up studies to identify plausible, non-biological explanations for the same spectral signal, including possible instrumental artifacts and alternative sulfur-based chemistry that didn't require biology at all. Decades earlier, in 1996, a team of scientists announced they'd found what appeared to be fossilized microbial structures inside a meteorite that had originated from Mars, a claim that generated enormous excitement at the time, even prompting public remarks from the sitting President of the United States. Later, more careful research demonstrated that the specific mineral structures used as evidence could also form through completely ordinary non-biological geological processes, gradually eroding scientific confidence in the original claim over the following years of careful, methodical follow-up research. It's worth spending a bit more time on this Hycean World idea, since it's central to why K2-18b generated so much excitement in the first place, well before the DMS debate ever started. Nico Madhusudan first proposed the Hycean concept as a way of expanding where scientists might reasonably search for habitable conditions beyond Earth. For decades, the search for potentially habitable exoplanets focused almost entirely on finding rocky, Earth-sized planets sitting at just the right distance from their star, essentially looking for direct Earth twins. The Hycean concept opens up a much larger category of candidate worlds, sub-Neptune-sized planets, larger than Earth but smaller than Neptune, that could theoretically host enormous planet-spanning oceans of liquid water underneath a thick, hydrogen-rich atmosphere. Because these planets can be significantly larger and can potentially orbit at a wider range of distances from their star while still keeping livable ocean temperatures beneath their thick atmospheres, Madhusudan's team has argued that Hycean worlds could realistically be common throughout the galaxy. Importantly, because of their larger size, they tend to be easier for telescopes like Webb to study in detail than small, rocky Earth-sized planets, which produce a much fainter signal when starlight passes through their comparatively thin atmospheres. K2-18b became the flagship test case for this whole idea, the first candidate Hycean world where scientists actually had enough high-quality atmospheric data from Webb to meaningfully test the concept against real observations rather than just theoretical models. Let's also take a moment on what these sigma values, the number scientists use to describe detection confidence, actually mean, because they come up constantly throughout this story and are genuinely important for understanding why the debate has dragged on so long. In science, a detection described as 3 sigma means there's roughly a 1 in a few hundred chance the observed pattern could have appeared randomly, just from ordinary noise in the data, rather than reflecting something real. That might sound reasonably convincing on its own, but by the standards astronomers and physicists generally require before confidently announcing a genuinely new discovery, especially one as significant as a potential biosignature, 3 sigma usually isn't considered strong enough evidence on its own. Many major discoveries in physics and astronomy, including the historic 2012 discovery of the Higgs boson particle, weren't officially announced as confirmed until researchers reached a 5 sigma confidence level, corresponding to roughly a 1 in a few million chance of the result being random noise. The original April 2025 DMS and DMDS announcement from Madhusudan's team sat right around 3 sigma confidence, which explains both why the team felt confident enough to publish and publicize the result, and why so many other researchers immediately treated it as an intriguing but far from settled finding. That's one that absolutely required independent verification before anyone should treat it as confirmed. Let's talk about why finding a definitive, universally agreed upon biosignature is such a genuinely difficult scientific problem in the first place, beyond just this one K2-18b debate, and why so many careful, well-trained scientists can look at the exact same numbers and still walk away with different conclusions about what those numbers actually mean. Many of the molecules scientists consider promising signs of life can, at least in principle, also be produced through completely non-biological chemical processes, things like volcanic activity, reactions between a planet's atmosphere and its surface rocks, exposure to intense radiation from the host star, or chemical reactions triggered by comet and meteorite impacts. At the same time, genuine biological activity on a planet could theoretically be completely hidden from telescopes like Webb, masked by cloud cover, diluted by low production rates, or simply produced in quantities too small for current instruments to reliably detect from 124 light-years away. Because of this fundamental ambiguity, most astrobiologists in this field have moved away from searching for any single silver bullet molecule that would instantly prove life exists somewhere. Instead, the field increasingly focuses on looking for entire combinations of molecules that would be jointly difficult to explain without some form of biological activity, essentially building a much stronger circumstantial case out of multiple independent pieces of evidence rather than betting everything on one potentially ambiguous detection. Now let's talk about the other half of this headline, the part specifically mentioning a signal being detected, because it's genuinely worth being clear about exactly what kind of signal we're talking about here, especially since plenty of online content tends to blur this distinction on purpose. What Webb detected on K2-18b is not, and never was, any kind of transmitted signal in the way most people picture when they hear that word. It's not a radio broadcast. It's not a beam of light being sent toward us on purpose. It's a spectroscopic signature, meaning astronomers analyzed how starlight from K2-18b's host star gets filtered as it passes directly through the planet's atmosphere during a transit, when the planet crosses in front of its star from our point of view. Different molecules absorb very specific, precise wavelengths of light, leaving behind a kind of chemical fingerprint embedded in that filtered starlight. Webb's instruments are sensitive enough to detect and measure those extremely subtle absorption patterns, and scientists then work backward from that pattern to figure out which molecules are likely present in the atmosphere. That's genuinely remarkable technology, but it's fundamentally different from detecting an intentional signal broadcast by some kind of intelligent civilization. And in fact, in March 2026, a completely separate research team directly addressed that exact question, specifically checking whether K2-18b showed any evidence of an intentionally transmitted signal at all. This team conducted what's called a technosignature search using two powerful radio telescope arrays, the Carl G. Jansky Very Large Array, usually just called the VLA, and the Meerkat Array, located in South Africa. Technosignatures are observable, measurable signs of technology, the kind of evidence a genuinely intelligent, communicating civilization might leave behind, most commonly imagined as narrowband radio transmissions, since a very narrow, precise radio frequency is considered an efficient, deliberate way for any civilization to try to signal its presence across interstellar distances. The VLA observed the K2-18 system across multiple separate days between late September and late December of 2023, while Meerkat contributed 3 additional observing sessions that same year, together covering at least one complete 33-day orbit of the planet around its star. This combined search scanned an extremely broad range of radio frequencies, from 544 MHz all the way up to 9.8 GHz, noticeably wider than most previous technosignature searches had covered, with sensitivity capable of picking up transmitters up to 1,000 times weaker than earlier searches could detect. After processing an enormous amount of collected data, more than 20 million individual detected radio signals from the VLA observations alone, the research team applied a careful filtering process. Since K2-18b is actively orbiting its star, any genuine, deliberately transmitted signal originating from the planet itself should show a very specific, predictable shift in frequency over time, caused by the planet's own orbital motion, similar to how the pitch of a passing ambulance siren changes as it moves toward and then away from you. Signals that stayed perfectly fixed in frequency across multiple different observing days without that expected shift were ruled out as likely originating from human-made technology here on Earth, radio interference from satellites, cell towers, or other terrestrial sources, rather than from anything actually located in the K2-18 system. After applying this filtering process across the entire dataset, the research team found no transmissions consistent with an artificial technological origin coming from the K2-18 system. So, to be completely clear and honest about this whole story, no radio signal, no intentional transmission, and no confirmed evidence of extraterrestrial intelligence has been detected from K2-18b. What has genuinely been detected, confirmed by multiple independent research groups using different methods, is a water-rich atmosphere containing methane and carbon dioxide, sitting on a planet orbiting comfortably inside its star's habitable zone. What remains, a genuinely unresolved, actively debated scientific question, is whether that same atmosphere also contains dimethyl sulfide, or a closely related molecule. These are chemicals that, if their presence were ever confirmed with much stronger statistical certainty, would represent one of the most significant potential biosignature detections in the history of astronomy, precisely because there currently isn't a well-established, non-biological way to explain how large amounts of DMS could accumulate in a planetary atmosphere. This is exactly why scientists working on this case have consistently stressed that more observations are needed before anyone can draw a truly confident conclusion either way. Because K2-18b transits its star relatively often, completing an orbit roughly every 33 days, astronomers have the opportunity to schedule additional Webb observing time specifically to gather more data, hopefully pushing the statistical confidence of any detected signal, whichever molecule it eventually turns out to be, well beyond the currently disputed range. Some researchers involved in this ongoing debate have suggested that fully resolving this particular question may ultimately require the next generation of space telescopes, instruments even more sensitive than Webb, specifically designed with exoplanet atmosphere characterization as a primary scientific goal from the outset. That's rather than as one application among many for an already extremely busy observatory that also has to split its limited observing time between early galaxies, star-forming regions, black holes, and countless other scientific priorities across the entire astronomy community. NASA has already begun early planning stages for a future mission sometimes referred to as the Habitable Worlds Observatory, envisioned as a dedicated successor specifically built around the goal of directly imaging and characterizing potentially Earth-like planets around nearby stars, though that mission remains years away from launch and wouldn't be expected to gather its first meaningful data until sometime in the 2030s at the earliest. For now, K2-18b remains one of the single most closely watched, most scientifically significant exoplanets known to astronomers. A genuinely fascinating world with a confirmed thick, water-rich atmosphere sitting at a comfortable temperature range inside its star's habitable zone, orbiting a small, quiet red dwarf star 124 light-years from Earth. Whether that atmosphere also happens to contain a genuine chemical signature of active, ongoing biological life remains an open, actively contested scientific question, one that could realistically be resolved with several more years of careful, patient, independently verified observation, rather than through a single dramatic headline claiming the mystery has already been solved. It's also worth remembering that even if DMS or DMDS is eventually confirmed with much stronger statistical certainty, that alone still wouldn't count as absolute definitive proof of life, since scientists would still need to rule out every plausible, non-biological explanation first. That's a process that could easily take years of additional dedicated observing time, laboratory experiments here on Earth, and careful theoretical modeling before the broader scientific community would be willing to call the case genuinely closed. That's simply how rigorous, careful science works when the stakes of getting it wrong, either by claiming too much too soon or by dismissing a genuine discovery out of excessive caution, are this enormous. If you want more of these deep, honest, fact-checked breakdowns of what James Webb is actually finding out there, rather than the exaggerated version that spreads fastest online, subscribe now, because K2-18b is almost certainly going to remain in the headlines for years to come as more data keeps rolling in. Drop a comment and tell me what surprised you most about this story. The fact that scientists still openly disagree about the exact same raw data set, the fact that a separate radio search already ruled out any artificial signal, the sheer number of independent teams that had to double-check this single result before anyone could trust it, or the fact that this same kind of high-profile claim followed by careful walkback has actually happened before with both Mars and Venus. Thanks so much for watching all the way to the very end. I'll genuinely see you in the next one.